Ladies and gentlemen, welcome to the Georgia Tech AI podcast. Today, I'm thrilled to introduce our guest, Sandilya Sai Garimella, a graduate researcher in the field of robotics and artificial intelligence. He's worked closely on one of the crucial challenges in robotics, multi-robot networks. He's exploring how systems can coordinate efficiently to tackle complex tasks, such as drone surveillance. He's also been involved in contact perception, using graph neural networks to reconsider how robots understand and interact with their environment. Imagine a world where robots can navigate in any terrain as effortlessly as animals do. Sandilya's research could one day make this a reality. Beyond his research, we'll also touch on the practical challenges of implementing these cutting-edge technologies and what it means for the future of industries ranging from agriculture to urban planning. So without further ado, please join me in welcoming Sandilya Sai Garimella to the podcast. Sandilya, it's great to have you here.
Yeah, thanks for having me, Kasim.
The area I'd like to start off with is your publication on multi-robot networks. We were just talking about the intuition behind such a system. Could you walk me through an example of a multi-agent system in nature?
Sure. So, we often see, a lot of animals in the natural world coordinate with each other to achieve a benefit that's much larger than if they just individually did the task. For example, we see this in ants, we see this in bees, but one particular example that comes to mind is a school of fish trying to evade predators, right? So there may be hundreds, maybe close to thousands of fish in the ocean, and suppose there's a dolphin or a group of dolphins trying to, catch their prey. What we observe is the school of fish are able to evade the predators almost effortlessly. It's, dolphins have to come up with a separate strategy as a multi-agent system to be able to catch these small school of fish. So if we think of just how each fish in the school is coordinating or thinking about its actions, we observe that a single fish actually doesn't communicate with every other fish in the school. It's actually just focusing on its immediate neighbors, and it's trying to follow the motion based on its immediate neighbors. So you have this kind of a if you think of the fish as a graph, as nodes, and each of their pairwise observations as edges, you see there's kind of it's not a fully connected mesh. And this works pretty well because if you have to communicate with every other fish in the school, it's really expensive, and you have to wait for hearing back from all the other fish, for example. And so you have this trade-off between like a guarantee for performance where you're evading your predators and your real-time performance. So in the research that I do, they call these like decentralized multi-agent or multi-robot networks, where each agent doesn't necessarily communicate with every other agent. You're focused on your neighborhood, and through each robot working with its own neighborhood, you achieve coordination that's comparable to that if it was fully centralized.
I want to delve into this difference between centralization and decentralization. So centralization, if I'm not wrong, is when the network is fully connected and all the robots receive information from all the others. But decentralization is when the network is fully disconnected. All robots receive no information from the other robots. Can you explain to me why centralization is a bad idea? Wouldn't that get me closer to an optimal solution?
That's a really important question. So the thing with centralization is, yes, it does it has better optimality guarantees, and by optimality guarantees we mean, say for example, you have a system, you have a number of robots, and you need to cover as much area of an unknown map, right? Let's say like map exploration. If they're fully centralized, every robot knows every other robot's actions, and so you can achieve a better guarantee that in this amount of time I'm gonna cover this, area. And it's generally better than if it was decentralized. But the reason generally we want to move away or improve this kind of coordination away from centralized almost is because centralization carries a lot of real-time performance shortcomings. Like one particular thing is the communication delays. So suppose you have a number of agents, and each of them are collecting, very rich sensor streams like RGB, depth, lighter 3D points. Transmitting those over your radio network introduces a lot of delays, because you have a fixed bandwidth and you have to communicate with so many different neighbors. That's one approach. If communication was made peer-to-peer, so vehicles are directly communicating with each other. Another thing is if you have a base station, right? Like you have one base station, all the robots transmit their data to that base station, and that's also centralized, right? Through the base station on the same host machine, you can let the robots get each other's data, but your base station would have to be very, very powerful, a lot of compute, right? And it's actually more vulnerable to attacks. Say you have a adversarial agent in the network, say that's being that was captured by an enemy or another phenomenon. If your base station is compromised, then all the agents are down. So at the cost of one base station, you've grounded the entire fleet of robots. So that's why we want to focus on having distributed or decentralized networks. So if even one robot has failed, the others can still continue to.
Yeah, I didn't consider the vulnerability aspect. It seems that centralization is not always the best idea. Could you also help me understand what is a critical point? In your paper, you mentioned that there's a critical point where the increase in decision time due to more centralization does not necessarily equal to more benefit from reduced action overlap. That's a pretty dense statement, so could you potentially unpack that?
Sure. So the idea behind the objective in that in this scenario, in this paper, is you have a fixed number of robots and they need to cover some amount of area. It's an unknown map. So essentially you want to, it's basically sensor placement, and you want to place these sensors in the environment over time. So they're actually dynamic. They have to continuously move and coordinate such that you cover as much area as you can in the least amount of time. So with this kind of a problem, you have I'm trying to explain this without directly jumping into submodularity, but I hope I'm able to build the intuition here. Okay, so the idea is the most simple example. I'm gonna tackle the question ultimately, but say you and me are robots and we have to cover as much area as possible in this room. We want to make sure we select actions that are not overlapping with each other. Because say I have a field of view and I observe this side of the area, it would be better if you in a way move as far away from me as possible and explore that area, so that over time when we stitch our map together we have a global map that has more areas that have been explored, right? So essentially, this was two robots, two humans, but as we add the number of robots, their marginal utility, meaning the additional benefit that you get from the observation of the extra robot decreases. So it's basically showing diminishing returns, right? So if you plot a graph on the horizontal axis, you have number of robots and their marginal utility on the vertical axis. As you add more robots, their increased utility decreases. So that's what, coming back to your question here, there's like this point where the number of added robots don't really benefit you a whole lot. So you can achieve the same or comparable results, but with fewer robots, because you're exploiting this submodularity in the phenomenon that you're observing, whether it's area coverage or simultaneous localization and mapping, SLAM. So that's what this paper, one of the punchlines, you can say, tells you.
So the second step of your algorithm is action coordination, where you limit each robot to coordinate only with its neighbors. So your algorithm is effectively reducing information explosion. However, let's take drone warfare as an example. Aren't there situations where drones need to know what drones that are very far from it doing? How are we accounting for this information?
Exactly. Yeah, it's actually, yeah, you definitely want to have knowledge or information from a drone that's much further away, potentially because it can be useful for path planning, right? Like if you have trajectories that may overlap in the future over your finite planning horizon, and you want to select trajectories that don't necessarily do that, so you still optimally explore the environment, let's say, then you would want to communicate with your neighbors that are not immediately, one hop, let's say. So here, so we don't explicitly communicate with neighbors that are outside of your communication range, and the reason we, like, in this problem, we put a communication range because if it were to, implement on real robots, we would have a realistic communication range of, say, anywhere between a few hundred meters to a kilometer. So the robot that's, say, 2 kilometers away or outside of your communication range, even if you want to communicate, you may not be able to have that information. But as the robots opportunistically get into communication range, we have, each robot decides, these are my candidate neighbors, but out of these candidate neighbors, I want to specifically choose a subset of those neighbors to coordinate with. And that's where we limit the number of in-neighbors. So you have everywhere from like no coordination, like completely disconnected, to up to 6.
So in your paper, you talk about 2 settings. One is with 15 drones and the other is with 45. However, all of this was done in simulation. So could you talk about the practical challenges associated with deploying this in the real world?
I'm so glad you asked this question because, yeah, the simulation, our simulation tries to incorporate these like communication delays like artificially, and we, simulate the data rate and the attenuation of the signals as the robots communicate. But when you have to implement this in real life, it's a completely, the sim to real gap we expect is going to be very large, and by that I mean you're going to have like the models or the sensor measurements that you get from the cameras and your IMUs, and they're like, the noise may not be Gaussian, for example. The noise manifests itself in different distributions, for example. The other thing is actually having the hardware to implement this with the real drones. So in the simulation, we have drones equipped with RGBD cameras, depth, semantic segmentation, and they have a gimbal that rotates. And having 15 or even 45 such drones, obviously there's a cost to do that. And the vehicle to vehicle communication. Like we're gonna need to use actual radio hardware, maybe something off the shelf that's used similar to used in the DARPA subterranean challenge, where they had entire systems specific for that kind of a task. But other challenges I expect, other than the communication itself between the agents with the radio, it's almost like you need a whole another set of automatons to coordinate this kind of experiment. Like, how do I obviously it's not a impossible task. It's you have to write a lot of ROS2, ROS1 code to enable you to take off the fleet, now perform the task, and land. And what do I do if one of the drones is damaged and it's crashed? There's also other safety factors you need to consider. So I think having this in a real life experiment would be really impressive, and that's what I'm looking forward to.
Your first paper was about a robot that was concerned with plucking dandelions from the ground. And in that, you would come up with this quote, this line that still is quite valid today. And it is, robots can evolve in one of two ways. They can become cheap, reliable, and moderately productive. Or they remain complex and expensive, but be spectacularly productive. What was your thinking when you came up with that line? Because it's still quite prevalent even when we're having this discussion right now about multi-robot networks.
Yeah, so I think, there's definitely like a red thread connecting the two, even with the first article that I wrote. So I guess the higher level idea with that project, and actually even the multi-robot networks, having them decentralized, is that we want to democratize access to robots. I mean, in the larger context, we see ChatGPT, all these like GPT models, everything. It's you can, if you have access to the internet, you have access to them. So that's like on the reasoning side, right? So there's like a paradox, I think it's called Moravec's paradox, where robots find reasoning tasks fairly simple. Like, say for example, chess, such a complex game, you have so many moves. A chess engine can think really quickly, and it can formulate all the best moves and so on. And its ELO ratings are usually 1,000 higher than even the best grandmaster. But when it comes to sensory motor skills like manipulation or actually interacting with the environment tangibly, that's where a lot of compute resources are used by the robot. Whereas for humans, it's almost a trivial task. But the other way around, where unless we train really, really hard our minds, we can't achieve the same level of mental capability, right? So there's kind of a strength and weakness imbalance there. So if we make robots, like physical robots, more accessible and more common in our world, we can, along with the, we can leverage both sides, basically, right? A human and robot. So with coming back to the legged robot project. So the idea was to use a 6-legged robot built completely out of a special kind of a styrofoam, if I remember correctly. Yeah, it was it's similar to insulation foam, but it's just a very thin, like a foam, basically, right? It's a foam board. So the reason for that is the cost of that robot is maybe roughly under $1,500, compared to if you want to get a legged robot. At that time, the most famous one was a Spot from Boston Dynamics. I think it costs close to maybe $30,000 for a single unit, right? I mean, of course, definitely it's much more advanced. The control of the legs, the robot, the sensor streams. It has 3D LiDAR, the depth cameras, and so on. But you have such a low-cost robot that's still able to move, and you can control it fully in the 2D plane. So if you have such a robot, can you use it in an agricultural setting where a lot of viable crop area is actually trampled by these large crop harvesters, right? Like you often see them, they're when they're harvesting the crop, a lot of it is trampled. So there is amount of food that's wasted there.
Right.
But can we use legged robots, especially the 6-legged big ant robot, to to work in an agricultural setting? So the specific scientific question that I was working on is more of a design question, where can we use this robot to basically control a lawn pest, which is dandelions, as a placeholder for now, without making it complex, without retrofitting a very complex mechanism for picking the dandelions and so on, and to also integrate some perception into it. So there was an RGB, there's actually a LiDAR camera on the robot, and you have RGB streams. So that's what the project was. And to the specific point that you mentioned, where robots can get really cheap and still be fairly effective versus expensive and spectacularly productive, right? This is obviously on the side where it's very cost effective, but its control and like the amount of sorry, I need to think about this carefully.
You say it's not that productive?
Yeah. So just compared to like if you have a level playing field for both the robots, it wouldn't be as productive as a spot robot dog. Yeah. So it needs more. So and that's where I came in and said, actually, you don't need another mechanism to actually pick dandelions. Right. There was this when it was walking. So it's a hexapedal robot, and it uses an alternating tripod gauge similar to an insect. It's actually a bio-inspired robot. Oh. So that's where I noticed when it was walking, it had this slight parasitic vertical motion. So I basically designed a trajectory which the robot can do once it has reached a target to pick up the object without any other appendages which move, right? Sure. So that was the very first robotics project that I started. There was also like a strong educational motive behind it, like getting used to how to integrate perception, control, those aspects. Yeah.
Could you talk more about this connection to nature? You keep harping on examples about how things are done in nature and how they're reflected in robotic systems today, be that the school of fish or dandelions or contact perception in legged robots. Why is it that roboticists have to account for nature, morphology, symmetry? Why is this important?
I think, to answer simply, I think nature does it really good. And if we can learn from nature, it's almost like taking a proven working idea and we're trying to just emulate that. And a lot of things that we see in nature, of course I have to say I'm not I say biology and like evolution is not my forte, but from what sort of keyhole I view it through and what I understand is that bio-inspired robotics benefit a lot, because you see that things that are done in nature they're not over-engineered almost, right? Like, and when we try to do them in robotics, you make sure that the implementation that you have isn't deliberately over-engineered. It's enough to make it work for the task that you want to do, but obviously it can be augmented and enhanced to improve that. So that's the reason why bio-inspired is a great idea to learn from. And then the idea about symmetry and the MIH GNN paper.
Before we go there, what
Yeah.
is MIHGNN?
Yeah, of course. Okay, I often I'm in this I'm in this bubble where I'm like, okay, but I need to yeah. I think it's because in our bubble, like when you're in this lab, you talk about it day in day out. So you need this kind of a perspective where you're able to explain it without complexity and jargon. That's what I really want to get better at, and that's what I want to learn and become better at. So anyway, coming back, MIHTNN is morphology informed heterogeneous graph neural network. So the high level idea here is you have a legged robot, and we do this thing called contact perception. So each of the legs, in this case, four-legged robot, they have sensors for measuring the force. So essentially, they provide you a vector with the force experienced by that specific leg in a certain foothold during stance or during its natural gait. And we want to come up with a solution so that as the robot walks, you want to predict based on the current state. Excuse me. What are the forces that are going to be exerted on the legs, on the feet specifically, in the coming time steps.
I see.
So there's multiple approaches, right? Of course, you have a dynamics model of the robot that's been established pretty well. Of course, that's how the control schemes, everything are executed. What we propose is to basically attach a node in a graph again for each sensor and each sensor in the robot structure. So the robot has sensors on its feet, and then at each joint there's a motor. The elbow, at the hip, at the waist, and so on. And each of these motors, we can measure the torque that's being exerted by these motors. So we form a graph neural network that mirrors the structure of the kinematic structure of the robot. And essentially, we train it using data that's been collected on different terrain. So flat terrain, sloping up and down, rough terrain, stairs, for example.
A quick aside, are these adaptable to varying terrains? Humans instinctively know when they're on uneven terrain and they need to pay more attention. How do GNNs, graph neural networks, generalize to unknown terrains?
It does require extensive training. I would say the out of sample, like if there's a terrain which you've completely not seen before, at least for now, the robots, legged robots generally still struggle to work with that. And the reason for that being contact perception and the way you model the friction and even the dynamics of the robot it's a very highly nonlinear and complex field. So in terms of generalizations, the terrain has to be not necessarily only in the sample that you've seen, but not vastly different from that. So for example, if I've trained it to walk on sand, obviously there's some slippage, right? The robot will be able to walk on gravel where there's some amount of slippage, or even finer sand, right?
Right.
But if you take it into a forest where there's a lot of leaves, there's more factors in which contribute to the robot slipping. If you train it on unless it's been trained specifically for that, it does not generalize to.
One of the challenges I keep reading about with regards to graph neural networks is that they're computationally expensive. As we get stronger, more powerful computers, is there a future of graph neural networks in the field of contact perception?
Yeah, so I believe, short answer, yes, there definitely is. I mean, of course, there's Moore's law, right? The amount of transistors we fit, it's definitely going to accelerate this. So online inference is going to get much, much faster. And that, of course, not as a consequence, the other way around, actually, that also means that the compute we use for training is also going to be more powerful. So for the same amount of time, we'll be able to use a lot more data train the neural networks to perform these tasks. So I definitely think it's it's definitely going to be very useful in the future, and it's not something that's like an academic excursion. I definitely think there's merit in this idea as a future. The thing with I wanted to say was, especially with the training, right? So of course, training the graph neural network, you require enormous amounts of data of the robot actually walking and collecting real life data sets. And if you wanted to generalize, as you were mentioning, generalize to different kinds of terrains, unseen terrains, those would kind of have to be in your set of almost seen terrains. So I think one of the bottlenecks is actually being able to collect this real life data with real robots, and having more people actually have access to these robots so that they can collect them and have a common platform on which, the encoding of the graph neural network, for example, has to be common, so more people can contribute to the training. One particular advantage, though, here is compared to, say, for the same compute, you have a very complex, very rich, high-fidelity dynamics model of the robot, and you're trying to predict the contact forces, right? You would be able to do that in real time, comparable to that of the graph neural network. But the dynamics model, my understanding is it takes longer time for inference in some special cases. Whereas the graph neural network, although it takes longer time to train, gather all the data, train it, the real-time inference is much faster. And we've seen these kind of performance improvements even for path planning among multiple drones and collision avoidance, things like that, where the longer time you spend inferring about the collision, you're already moving, and changing your path direction is going to be more costly and can lead to a crash. So
Right.
things like that.
So rounding out this conversation, I wanted to ask a bit more of a personal question. You studied mechanical engineering and then eventually moved into robotics. There's definitely this emphasis on having an interdisciplinary mindset. Could you talk about why having this broad range is important if you want to be a roboticist?
Sure. So, yeah, coming from a mechanical engineering and an electrical engineering background where I focused mainly on dynamics and control, coming into robotics, I initially found, I have to admit, the jump into programming, I found it quite challenging. And I have to say, this is before the ChatGPT era.
Okay,
So,
one of the real ones.
yeah, this is the Stack Exchange era. I think it's still, I still love Stack Exchange. But so coming from that background, I found it a steep learning curve to get into programming. But I was really lucky to have a graduate student as a mentor and another professor where I was able to get advice and get feedback so I could improve. But the main thing was programming skills, coming from using MATLAB, which I think a lot of people think of MATLAB as a lesser language, but that also, I want to talk about that at another point, is so object-oriented programming using Python and C++, I had to build those skills mainly through a master's program. But if you're coming from an undergraduate background, that should be sufficient. And the important thing for me was how interdisciplinary it is. You want to solve a problem. Instead of viewing tools as ideologies, I tried to view them as simply as tools which you can use to solve problems. And in that way, instead of pigeonholing yourself into a certain kind of way of solving a problem, you see what can I adapt from this or what can I use from this that's the most useful and build on that. So that's one important thing. Another thing is mathematical background. I think robotics is of course very vast, but linear algebra, probability statistics, these things need to be strong. And one thing I used to do was especially in my undergrad, I have to admit, I used to mostly parrot facts, right? For example, like, why is Bayesian optimization optimal, or all these kind of things, and always be okay. But as I came into grad school and started the PhD program, I tried to really spend time, pen and paper, reading a textbook or online, focusing on the fundamental mathematical, concepts and theorems, and doing examples. And I also worked with them through a mentor who was, in the PhD program, and that really helped me a lot.
What are the motivating questions for you as you pursue robotics research?
Okay, so, that's a really deep question. I feel like I think about this time to time, but yeah. So for me, like the idea of intelligence and what we're trying to do with artificial intelligence and robotics is not necessarily to replace the human at this stage, for now. It's to actually augment the human's capabilities and have insights which a team of humans cannot have. So yeah, in a nutshell, yeah, it's not to replace the human entirely, but to focus on how to give the human the edge, and how to either increase productivity or save time. Like, so you have the time value of money is saved, for example, to tackle problems in the real world. Like, specifically I focus on like search and rescue, exploration, persistent surveillance, for example. But I feel like I myself am not, I have to admit, I'm maybe not very satisfied with my own answer. I feel like there's a deeper question here.
What are the moments that give you the greatest joy while working on your research?
Oh, yeah. So I want to, like, the main thing that motivates me is when I'm able to see an idea that was abstract, and it was initially, say, on a whiteboard or just, back of the envelope, right? And I see that idea come to fruition in the form of a real robot doing an actual task, or in a simulation where you have certain guarantees and, they can fairly transfer to real robots. Seeing that really motivates me in a way, because it just means, given what we have or current resources we have, we're still able to make these advancements, not through huge leaps in like entire, like not like in a paradigm. For example, like communication was through letters, but then once radio came on, it was a completely different shift. But I think we don't need necessarily such a huge paradigm shift overnight or instantly to have such a profound impact. It's just, yeah, the motivation is being able to use and optimize the concepts that we have to increase the ability of the existing machines. And of course, with that comes those huge leaps, right? But yeah, that's what motivates me.
Sandilya, it's been an absolute privilege speaking with you. I wish you all the very best in your future research. Thank you for your time.
Yeah, thanks. Thank you for having me. Yeah.
Thank you very much.